Hello all, welcome back to our channel, and today's topic is quite interesting. We are going to talk about an operational amplifier's offset voltage. Offset voltage. So in particular, we will talk about input offset voltage, and we will also see how what this input offset voltage is and how this offset voltage at the input causes an offset voltage at the output. So there are two terms, offset voltage at the output. So this is an amplifier circuit. We see that an amplifier with an open loop gain AOL, and it has a negative input and the positive input, and then it has an output. Then it has a power supply rails, and obviously at the positive input we are applying this input signal, voltage or current, and at the negative input we have this resistor RF in a feedback loop, and then R1 is also connected in this fashion. So this is basically non-inverting amplifier. In our previous video, we have seen this explanation. So you might want to refer to that video if you want to understand the working principle of it. And the output voltage, which is right here, is given as is equal to 1 plus RF over R1 multiplied by V in. That is your input signal. And we can see that the RF and R1 is set as given. Therefore, it is 9 over 1. And that comes out to be 10 times the V in. This is the V out. So if the V in is 1 volt, V out is going to be 10 plus 1 is equal to 11 volt. So this is how the non-inverting amplifier is working. But what about the offset voltage? Offset voltage is the voltage difference between positive and the negative, or between negative, the voltage at the negative and the voltage at the positive, either way. Is the so VOS, if we define that, so it is defined as the voltage at the positive minus voltage at the negative. So that's how we can refer to it. Or it can also be written as taking the magnitude V in negative minus V in positive. Okay, voltage at the negative input and voltage at the positive input. Now, in ideal operational amplifier, the value of VOS is equal to 0 in ideal case. So it means there is no differential voltage between the two terminals of the amplifier, and therefore the output is basically gain times VID. So if the offset voltage, which is the difference between the two inputs of the op amp, is 0, then output will also be 0 if VID is equal to 0. In such case, when you apply a V in with the value as given right here, and then you have this feedback arrangement, so output in this situation is given by 1 plus RF over R1 into V in. However, if there is an offset voltage present, then expression for the output would be 1 plus RF over R1 multiplied by V in plus 1 plus RF over R1 multiplied by VOS. So the output will also have a contribution from this term. Therefore, we would say V out would be 1 plus RF over R1 in bracket V in plus VOS. So you see that your gain, your offset voltage, which is the differential voltage between the two terms, is also getting multiplied by the gain. So without an offset voltage, the gain is 10 and the output voltage will be 11 volt, right? But just a second. But if you have an offset voltage with a value, let's say VOS is approximately or equal to 1 millivolt, then the gain of an amplifier is 10, which is set by this term 1 plus RF over R1. It will be multiplied by the offset voltage, and the output due to offset input offset voltage, the output due to input offset voltage will be 10 millivolt. And this is called as output offset voltage. So input offset voltage causes output offset voltage, right? So the total output, here we will see the total output V out total will be V out due to this V input and V out, which let's call it V out 1 plus V out 2. V out 2 is this one actually due to this term VOS. And it can be given as initially you have this 11 volt output, which is required plus 10 millivolt. So 10 millivolt is extra that you have. So output would be 11.01 volts. So in case of a precision design where amplification is to be precise, so you don't want such effect. You don't want the undesirable effect on the output of the signal. Okay, so we are going to demonstrate you that. So how and what we will do here is I will show you, right click the operational amplifier, that is a macro model. And here in earlier videos, we have explained to you that how to set up these values. So I have chosen open loop voltage gain to be 10 mega. Gain bandwidth of this amplifier is 10 mega. And VOS, that is an that is an offset voltage, output offset voltage, is that is an input offset voltage. Basically, you can say that VOS, which is the difference between the two input terminals, it is set to be 0. So if it is the case, if I apply 1 volt and a gain is 1 plus RF over R1, which is 9 divided by 1, which is 9 plus 1 will be 10. Gain is 10 multiplied by this 1 volt. I have an output of about 10 volt. So if that is the case or not, we will see. So what I'll do, I'll click simulate, edit simulation command, and I would select DC operating point with a dot op syntax. I will place right over here. And now I can just click simulate. So I am having the output voltage of 9.999 volts, which is very close to the desired output of 10 volt. So I expected, oh, not really. 9 plus 1, 10. Here output is 10 volt actually. It would not be. So this is 9 plus 1, 10 plus into 1. It's not 10 plus 1. It will be into 1. So 11, it should be 10 volt. And therefore this total output will be 10.01 volts actually. Okay, so let me correct that. And we are getting the 10 volt here. That's correct. Now voltage at the terminal V1, which is, let me take you here. This is the node. Because of the gain is 10 mega that we have set, the voltage at V1 will be equal to voltage at the V2, which is this node at the positive, and voltage at the V2 is V in. Therefore, this V in will come here. Okay, it's called as virtual short. It's the concept of virtual short. And that voltage is 0.999. So it's 1 volt. So approximately it is. So you see the op amp is trying, the amplifier is trying to force both the inputs to be equal, right? And rest are your current through the resistors and all that. Now, what I want to do is simulate an effect of offset voltage. So remember, output voltage is 9.991, which is theoretically close to what we calculated 10 volt, and the voltage at the V1 is 0.999. So we'll also see if this voltage and this voltage changes due to addition of the offset. So I am going to have the addition of the offset. It is 1 millivolts. That's what, no, it is 10 millivolt in theory I have taken. So I will choose that. Then click OK. Now I will run the analysis again. Here I go. Now the voltage is at the node V1, which is right here, was changed from 0.9999 to 1.01 because that's the voltage that I added. And the output voltage got changed from 9.9999 to 10.09. So output voltage is also increased. So there is an increment in the output voltage because of the input offset voltage. You have an output offset voltage along with the regular output voltage. So in a precision amplification, you want to avoid this effect. So there are manufacturers who manufactures precision op amps with the specific parameters such as very low or ultra low offset voltage. So in a precise applications for amplifications and some other parameter applications, designer often choose an amplifier op amp with very low or ultra low offset voltage. Okay, so remember again, the input offset voltage causes output offset voltage. So this is how the case is. Now, what is the reason behind having this mismatch between the two different voltages at the positive and the negative node? So inside the operational amplifier, all we have is your differential structure. So here you have, let's say, this is your register R, and you have this is also your register R, and then there is this active element or the semiconductor devices that we have, and this is another register. Let's say you have this RE and this one. So this is your transistor Q1, this is your transistor Q2, this is your positive supply, and that's your ground here. So this Q1 and Q2 should be equal. Q1 and Q1 or Q2, they are either BJTs or JFETs or MOSFETs. So ideally, the Q1 and Q2, due to fabrications, after fabrications, they should be equal. Their parameters should be equal. However, due to manufacturing tolerances, and you have a changes, the two devices are not exactly equal, and therefore registers are also not equal, and therefore you have mismatch amongst the components and the devices. Therefore, you have this output voltage always appearing at the terminal, even though there is no external inputs, even though the V in is equal to 0. which is in the case. So I am going to show you now the effect of offset. I have shown you how the offset voltage is reflecting in the output. Now I will set the V in to be 0 and I will show you what happens. So for example, let me clear the drawing here. Now we will set the input voltage to be 0, 0, and we will also set the output to be 0. That's the case. Now you have to tell me what is the output. What could be the output? Is pretty simple. When there is no input, the voltage at V2, let's do a very good analysis here. Here the node voltage is V2. This is your node voltage V1, right? So V2 is equal to V in is equal to 0, and therefore V1 is also equal to 0 if the AOL is very large. Okay, ideally infinite, ideally, right? And because it's ideally infinite, but practically it has a value of only 10 mega. Therefore, we used to, in the operating point analysis, we saw some potential here, right? About very low value of it. So now we have V in is equal to 0. Therefore, V1 is also is equal to 0. Essentially, there is no input at the negative and at the positive. Therefore, ideally, V out is equal to 0. So let us simulate that effect if that is the case. So we will just click the simulation button here. Let me just go. And here you are, output is still present, and we have to figure out why is that output coming 0.0001. So it's 0.1 volt we are getting here, and the voltage at the node V1 right here is pretty low. It's about 10 pico volts. So let's right click here, and we have this like output offset voltage set to be 0 volts here, right? So that's not the output offset voltage, it's the input offset voltage. So if that is the case, we see that we have the output voltage. Yeah, it's close to 0. Basically, we don't have any output voltage. So it's about just 0.1 volt. But if we set now this voltage to be about 10 millivolt, 10 millivolt, so we'll see how much is the output voltage. Now you can see that it's about 90 millivolt, right? 99 millivolt actually. 99 millivolt, and this voltage at the node V1 is also 0.0009. So it's reflecting the output offset voltage effect is being reflected. If you increase it further, let's say about 100 millivolts, you will see that. So here it is, output is now 99.99. So it's about just approximately 1 volt. So just because of with the 100 millivolt, your gain is actually getting your gain, which is 1 plus RF over R1, is getting multiplied with this offset voltage to reflect at the output. That's correct. So usually in a practical op amps, you have like offset voltage in the microvolts range, very tens of microvolts. And if it is ultra precise, ultra low offset, then even few microvolts. Okay, so that was all about the mic offset voltages, input output offset voltages. So hope you found this useful. If you did so, click like button, share with others. Stay tuned for informative content. Wish you happy learning.